Korhan and Louise challenge each other to find an estimator for the mean mu of the continuous random variable x, which has a variance sigma squared. x1 to xn are n independent observations taken from x. Korhan's estimator is given by this expression just here, and Louise's estimator is given by this expression just here. In part A, we're asked to show that K and L are both unbiased estimators of mu. So let's start with Korhan. Now, how could we rewrite this? We could rewrite it as 2 over n plus 1 x1 plus 2x2 plus 3x3 and so on up to nxn. So the expectation of k would be, well, since all of these things are independent of x, so it'd just be numbers in any particular case, we can just put those in front. And then we'll have the expectation of x1 plus twice the expectation of x2, and so on up to n times the expectation of xn. Now, all of the expectations are actually the same because they're from the same distribution. They're all expectation of x. So we could take all of those out as a common factor. So we've got twice the expectation of x over n plus 1. And then we have 1 plus 2 plus 3 up to n in here. And remember, expectation of x is mu, so that is 2 mu over n plus 1. In the bracket there, what we have is the sum of an arithmetic series with a equal to 1 and d equal to 1. And so we can say that that would be n divided by 2 into 2 times a, so that's 2, plus n minus 1 d. And so that gives us 2 mu over n plus 1. And this one gives us n plus 1 divided by 2. So when we cancel everything out, we just get mu. So now let's look at Louise's. So she has x1 plus x2 over 3 plus x3 through to xn over 3 n minus 2. So the expectation of L is going to be expectation of x1 plus expectation of x2 over 3. Well, that's just 2 expectation of x over 3. And then if we look at this lot, there are n minus 2 x's up there. So that's going to be n minus 2 e to the x's over 3 n minus 2. And e to the x is mu, so we have 2 mu over 3. n minus 2's cancel here, so we have plus mu over 3, and that is 3 mu over 3, or just mu. So they are both unbiased estimators. Okay, so in part B we want to find var k to start with. So this is B part 1. Now we know that k is 2 over n plus 1. And then in here we had x1 plus 2x2 plus and so on up to nxn. n. Okay, so if we want var k, remember it's a squared quantity, the variance. So that's going to give us 4 over n squared n plus 1 squared. And then we'll have var x1 plus 4 var x2 plus 9 var x3 and so on, all the way up to n squared var xn. Now, just as we did with the expectations, all these variances are going to be the same. So what we can do is take them out of there and we'll change it to sigma. So it's going to be sigma squared like so. And in here we're going to have 1 plus 4 plus 9 plus and so on up to n squared. It's the sum of the first n square numbers, which from the formula booklet is just this. So we've got 4 over n squared n plus 1. I dropped the squared there on the last line. Got to be careful with these things. Sigma squared. And then in here we're going to have 1 over 6 n plus 1 2n plus 1. So an n will cancel here. An n plus 1 will cancel here. And the 4 and the 6 can simplify. And so what we get is 2 times 2n plus 1 over 3n n plus 1 sigma squared. Now we'll do the same thing with the L. It's a little more straightforward. So our L is, well, let's just go straight to var L. We had the expression before. So we've got var x1 plus x2 over 3 plus var x3 plus x4 plus and so on up to xn all over 3n minus 2. Now remember the variances of x1, x2 and so on are all the same, they're just variance of x. So this first one, we've got 2 of those x's being added. That's going to give us 2 var x. But this 3 is actually inside here. Variance is a squared quantity, so that needs to be over 9, 3 squared. And then we need to do the same sort of thing over here, where we're going to get n minus 2. Remember there's n minus 2 of these in here. So it's going to be n minus 2 var x's. But we have to square the 3 and the n minus 2. Like so. Now we can change those to sigmas. So 2 sigma over 9 and n minus 2 sigma over, sorry, it'd be sigma squared, won't it? Over 9 n minus 2 squared. And of course the n minus 2's will cancel like that. And then we'd like it to be over a common denominator, so we can have 2 n minus 2 sigma squared over 9 n minus 2 plus sigma squared over 9 n minus 2. And if we simplify that, expand out and simplify, the top becomes 2n minus 3. The bottom is 9n minus 2. And then we've got the sigma squared. Now we're told for the last part of the question, the winner of the challenge is the person who finds the better estimator. Determine the winner of the challenge for large values of n and give reasons for your answer. So if we go back and we look at the variance of k, on the top there, the highest power of n is 1. So we've got n to the 1. But on the bottom, we've got an n squared. So for large n, so as n tends to infinity, the variance of k is going to tend to 0. But if we look at this one, we've got just n to the 1 on the top and n to the 1 on the bottom. And as n tends to infinity, the variance of L will actually just tend to 2/9 of sigma squared. So if you think about expanding out 2n minus 3 over 9n minus 18, when n tends to infinity, we can ignore those, and it's just 2n over 9n, which is 2/9 times sigma squared. So smaller variance is better, so k is the better estimator.